Example 8, this is a question from the 2023 exam, question number 4. So it gives us the derivative graph f prime, and it's asking us questions regarding the concavity of the original graph f. So how we can relate the derivative graph to concavity is that when it is sloping up, when the first derivative is sloping up, so in this case here, if we take that section there, it's sloping up. That means the derivative of the derivative, or the slope of the derivative, is positive. So that's going to relate to a positive concavity. If it's sloping down, okay, so in this case here, sloping down, that's going to relate to negative concavity. So that's going to be negative concavity there and positive concavity in this section here. Okay, so then I can just start making my chart here. Now it's going to be based on where it changes direction. So one place where it changes direction is going to be at x equals 0. Okay, we have an undefined second derivative there, so the slope of the derivative is undefined. But we know on the right-hand side, on the left-hand side, it is sloping down. That means it has negative concavity on that side. On the other side of that, we know it's sloping up, so we know it has positive concavity on that side. So it have negative concavity from, it looks like -2 is the end point, -2 to 0. The next place it changes direction is going to be at x equals 4. Again, that is an undefined slope there because it's a kink, but it changes direction. So those changes in direction would then indicate inflection points. So it's going to have negative concavity through there. So now we have the intervals from -2 to 0, from +4 all the way to the bottom here where it's going to change direction again. So that's going to be at x equals 6. In this case, we have 0 slope, so the second derivative would be equal to 0. And again, changing direction, we have now positive slope, which indicates positive concavity. Okay, so the intervals that it is concave down is going to be from -2 to 0 and from 4 to +6. Those are my two intervals. In part B of this problem, we're given the fact that f of 2 is equal to 1. So that's kind of our starting point. And we're given a value, we're asked to evaluate the limit as x approaches 2 of 6 f of x minus 3x over x squared minus 5x plus 6. So first thing to recognize is we do have a starting point. We do have area. So if we need to, we could work out y coordinates of this function. In this case, we don't really need to because we're going to plug in x is 3, and that's the only f we need to evaluate. And we've actually been given the value of f of 2 equals 1. So in this case here, we're going to evaluate this limit by plugging in x is 2. So we end up with 6 times f of 2 is 2. F of 2 is equal to 1. Okay, and maybe I'll just color code this. Just do this in a different color here. So 6 times 1 minus 3 times the 2, which is the x that we're substituting in. And then in the denominator, we end up with 2 squared minus 5 times 2 plus 6. Okay, so we end up with 0 over 0. Okay, so we can evaluate that limit. However, we do have the condition to apply L'Hopital's. Okay, so we're going to apply L'Hopital's here, but now when we apply L'Hopital's, we're going to differentiate notation. So in this case here, we get 6 times f prime. So f prime is the derivative of f minus 3, the derivative of 3x is just 3, and in the denominator, we're going to end up with 2x minus 5. Okay, so now we're going to try to evaluate this limit. So we need 6 times f prime at 2. Well, what does that mean? F prime of 2. Okay, that means the slope of f at 2, or the y-coordinate of the f prime graph that we have up here. So that's going to be 0. Okay, so I'm just going to fill this rest of this in before I put in the 0. So this becomes 2 times x is 2 minus 5. So evaluating this, we get 6 times f prime at 2, or the y value of the f prime graph at 2 is equal to 0. Okay, so it's going to be that point there. So we're going to plug in 0. So we end up with negative 3 over 4 minus 5 is negative 1. So the value of the limit is equal to 3. For part 9, example 9, we're just looking at continuity and differentiability. So in this case here, we've given a piecewise function, and this is evaluated for all values except for the top part is evaluated for all values except for 2, because we're dividing by 2. And this other part of the piecewise function defines the value of 2 for x equals 2 to be k. And we want to know what values of k is going to make this continuous. Well, this happens to be a linear function when you cancel these out. Not that you really need to know this, but it's a linear function. Okay, it's got a slope of 2, y-intercept of 1, and at x equals 2, there's a hole in the graph. Okay, and we want to fill that hole with this value of k. So for if we fill in that hole with k, we will make this continuous. So we need to know what value of k that is. So we need to then plug in x is 2 into this line to be able to work out the k value. So k is going to be equal to the y-coordinate when x is 2. So just plugging in that 2 value here. X is 2. And we can then just work out plus 1. And we can see that these terms cancel out. So we're just plugging into that. So k is equal to 5. So when k equals 5, this makes this continuous. And all we're doing is we're filling that hole in to make this graph continuous. Example 10. The function f of x is defined by f of x equals the square root of the absolute value of x minus 2 for all real values of x. So which of the following statements are true? So first thing we probably want to do is establish what does this function look like. Okay, so really we know that this is a square root function, and the absolute value is just going to mirror the square root on the other side of the y-axis. So the picture that we should really be thinking of when we do a problem like this is we have our square root function from a vertex at 2, and our square root function going this direction, and because the absolute value is going to mirror itself in this direction. Okay, so there's our x equals 2 vertex. Okay, so let's look at these statements. F is continuous but not differentiable at x equals 2. Well, it is continuous and not differentiable at x equals 2. Well, that is actually a true statement. Okay, so that's a true statement. So we're going to put a check next to this. So f is continuous but not differentiable because of the kink at x equals 2. For b, f is differentiable at x equals 2. Well, that would be not correct because there is this kink. Okay, so that is a big X for that one. There's a kink at x equals 2. F of f is not continuous at 2. Well, again, that's not true because we know that there is a vertex, there's a point at 2. So although it's not differentiable, it is continuous at that point. D says the limit of f of x going to 2 is not equal to 0. Well, in fact, it is equal to 0 because it's right on the x-axis. So again, this is not true. And then lastly, E, x equals 2 is a vertical asymptote of the graph of f. Well, that's not true either because there is no asymptote. Now, it does happen to have a vertical tangent at that point. Okay, so there is a vertical tangent that does exist there. What color should I choose here? I'm just going to choose yellow. There does happen to be a vertical tangent here, but it's not an asymptote. Okay, it's just a tangent, so we're going to say that this is also not true. So the only true statement is going to be A. Okay, it is differentiable, so it's continuous, but not differentiable because of the kink at x equals 2.